mouthful that was that full title. So we're tuning into the Stick Slip channel, looking at observations of both seismology and hydrology at Saskatchewan Glacier. And so this has been a huge amount of work done by myself, my collaborators here at University of Wisconsin, and at Penn State as well. And so before I go any further, I want to acknowledge the First Nations whose land my institution, my collaborators' institutions occupy, and the First Nations communities of North America who have shared ancestral lands with our field sites. So they're listed here. So this is a story about glacier hydrology and seismology. So we can start off with a very simple glacier hydrology box model, which we'll touch back on throughout the talk. So we initially have surface melt and rain that comes from the surface, enters into moulins and crevasses, travels through the glacier, and enters into channels, flows along the channels, and discharges out the front of the glacier. There can be exchange between the channels and cavities. So these small pockets of water that connected through networks of little channels to either side of, and they can store water and flux water in and out. And there can also be fluxes from the channels back into the moulins or crevasses, depending on the pressure at the bed of the glacier. And so we can monitor moulins, and we can monitor the front of the glacier, and we can monitor the inputs of water to try to constrain what is our hydrology doing. Now, in this case, we're particularly interested in looking at stepped bedded sliding. So I'll run through the basics of this that will become very important as this goes on. So the size of these water-filled cavities that form in the lee of bedrock steps and the corresponding contact areas, so this ice bed contact where there isn't water in between it, is modulated by the size of the bedrock step, sliding speed of the ice, and the relative pressures between the overlying ice, so this overburden pressure, and water pressure within the cavity. And it's these contact areas that modulate how much resistance to flow there is, so how much sliding resistance is there. This becomes important as we start to look at classic numerical theory, so the words of Alma Eken, and more recent experimental results of Zoot and Iverson that show that there's a little bit of a disagreement on what should these beds be doing. So as we look at this plot over here from Zoot and Iverson, we've got shear stress for the strength of the bed on the vertical, and we've got sliding speed on the horizontal. And within Eken's framework, it says there should be some maximum strength that the bed has, regardless of the sliding velocity, and as related, the pressure in these water-filled cavities. And so we should wind up with stable sliding, mostly regardless of the speed. So there shouldn't be many ice quakes in this case. But lab experiments from Zoot and Iverson show that as we increase sliding speed and we shrink those ice bed contact areas, the strength of the bed goes down. So this is called rate weakening, and is very much associated with the occurrence of stick-slip seismicity and tectonic faults, as well as glaciers. So looking at, what is the landscape of trying to find basal ice quakes? This comment from Podolsky and Walter in 2016 in the red says that these events are rather rare at the base of alpine glaciers in North America, but they are fairly prominent features in polar settings. They also comment that basal seismicity may not be related to stick slip, but community understanding really has shifted in the last 7 years or fewer years since Walter et al. That really we are looking at stick slip mostly. So it brings us to the motivating questions of this study. Is glacier sliding over step-shaped bed forms stable in a natural setting? If there is seismogenic unstable sliding, where and when does it occur? And more importantly, in what context does it occur if it's present? So to go ask a real glacier, what does it think about these questions? We went to Saskatchewan Glacier in Alberta, Canada. The reason that we picked it is shown right over here in this picture. So these are exposed, glacially carved, step-shaped bed forms on the scale of decimeters to multiple meters that were formerly underneath the ice as little as 50 years ago. So it's fairly sure that we have these continuing underneath the glacier because it's the same rock formation throughout the valley. And what we did is many of us went out in August of 2019 and we installed 32 nodal seismometers into the ice surface. We established a continuous GPS station. We instrumented a moulin with a pressure transducer. We set up a stream staging gauge here, and we monitored ablation across all of these sites, as well as recording air temperature and rainfall to give us this big picture of what is the hydrology dynamics and seismic emissions of the glacier. And so what we found is this. We recorded over 250,000 events that appeared to be basal events, and over 55,000 of those are well located near the ice rock interface. So we have this elevation view cut down the glacier, so we're going flow from A to A prime, and our ice rock interface shown here is from using more up-to-date methods than the methods used in 1952 by Meyer et al. And we can see that the large majority of these events are clustered nicely around the bed. So we have basal seismicity and we have it in abundance. And for comparison, we can look at another study that looked at a similar sort of setting, but for the Greenland ice sheet. And in 40 days, as opposed to our 18 days, they saw 11,000 events. So this has anomalously large amounts of basal seismicity. So for question 1, check. We do indeed have unstable sliding occurring for a stepped bed glacier. So then the where and the whens for question 2, and as promised in the title, here's our channel, that we have basal events clustering in this map view along the course of what appears to be a subglacial channel. It's along the bed, it's in the right position to receive water from these active moulins as well as this crevasse field. And from our bed mapping, the brightest clusters here, so these bright red saturated areas, correspond with areas that may have adverse bed slopes, where stresses are going to concentrate on that ice rock interface. And then in time, we have this time series of basal seismic rates. So we have number of events divided by 5 minutes for the vertical, time progressing throughout our study over our 18 days of recording. And we can see these beautiful diurnal cycles across different segments of the record, but they're vastly modulated in scale. And so we can go and interpret these. We can chunk them up into a few different periods, that we have these sets of diurnal cycles, period 1, period 3, and period 4 potentially going on if we'd kept the instruments running. And then they all have this feature that they start up shortly after solar noon. And then we have this one strange cycle that we've called 2A. And this initiates 5 hours before solar noon. And as we continue through the presentation, we'll continue to see why 2A is strange. And we haven't quite figured out what's going on there. So we're visiting our questions again. If there's unstable sliding, where and when does it occur? It appears to occur in the proximity of our subglacial channel, and seismicity is generally enhanced in time with diurnal insolation cycles, but rates are modulated over orders of magnitude across these multi-day periods. So we have to ask ourselves the question then, what's doing the modulation? So we turn to hydrology, and we start from the beginning. Let's start from the inputs and build our temperature index model using the methods of Regina Hawk. So we take our air temperature measurements from the toe of the glacier, we take our ablation measurements and sort out a estimate of the average melt factor to convert our air temperature into quantities of melt per unit time, divided by that sampling time, and we have a meltwater production rate. And we can add that directly to rainfall. And then we can take that sum, and since we're looking for multi-day trends, we can run a 24-hour rolling average across this and see what are the longer-term trends that are occurring in our, I apologize for the cat. So we can do a rolling average to look for longer-term trends. And so then we turn to our moulin and we say, okay, let's get a sense of the state of the glacier and how the subglacial pressure is evolving. So we take the record from our moulin transducer, corrected for atmospheric pressure, and we get a record that looks like this. And then finally, we have our stream stage record, and this will give us at least a measure of relative discharge since we weren't able to establish a grading curve. And so a couple of pieces that will come in to play a little bit later is that we had a power loss here for a thunderstorm. So this thunderstorm, based on the moulin hydrograph, probably produced as much surface water supply to the glacier as one of these diurnal cycles. So we may actually interpolate across this little valley here shown in the meltwater supply in the top frame with that question mark, that it's actually a continuation of that rising trend. And then down here for the stream, we had a cold snap, and the stream transducer became exposed in the air So we lost the record there, but it's likely a very low water stage. So we can set our seismic cycles back on top of this, and we can start to interpret, where do we get common trends through our hydrology. And so starting off with the water supply, we see that for periods 1, 3, and 4, we have a rising surface water supply rate throughout these cycles and progressing into the cycle. So we're putting more and more water into the system when there's more and more seismicity on progressive days. So you can see 2A is a bit of an oddity here because water supply is falling. We then look at the Moulin stage and we see that the variability, so the range of values within a given 24-hour cycle, is increasing through period 1 and progressing into period 3 when we have records. And finally, we look at the stream stage and we can see that progressing into period 3 and through period 4, we have increase in stream stage. And so coming back to cycle 2A and its oddness, water supply is decreasing, and we don't have that same increase in Moulin stage variability. So again, it's a bit of an oddity. So we've finally come back to our third question, say, if seismogenic sliding occurs, in what context? And this is one of the take-home messages I want you to have. It appears that it's not strictly associated with high basal water pressures, but instead it's associated with rising and highly variable basal water pressures. So what's going on in one of these seismogenic periods? So this is the picture that we think that we have. As water input rises, we increase basal water pressure, and this grows our cavities that we had before in that first picture. So this grows subglacial storage, and it makes the system less sensitive to water inputs for pressure variations. This also shrinks the ice bed contacts. Then with the larger cavities, we have a more connected subglacial drainage network, so more water can flow through the system with greater speed. The water input then overfills this expanded network. Water pressure goes up across larger parts of the bed than it could before at greater speeds. And more cavities expand, further growing water storage and further shrinking these contact areas. We've now primed the system for seismicity. And so what we have is when water input starts to drop, the network drains rapidly because it is well connected, crashing water pressures across large areas of the bed. This is signaled by this high variability in Moulin water levels and large discharges. The sliding of the normal stresses are concentrated on these diminished pieces of ice bed contact, and this loads the system to favor unstable sliding, producing the ice quakes observed. So we can then say, do we see this elsewhere? And in fact, in one of the great first studies of doing glacier hydrology and good seismic recordings, we see for Greenland Glacier by Walter et al., that they have this transition across a lake drainage event where they have this high water pressure and high water pressure variability associated with bursts of seismicity as the system starts to drain on these diurnal cycles. And then following the lake drainage, variability drops and seismicity disappears. So in fact, we can see a similar motif for Saskatchewan Glacier when we go from period 1 into this quiescent period where we have this high variability and high pressure dropping to low variability and lower overall water pressures. So in conclusion, we have observations of anomalously abundant seismicity in the bed of an alpine glacier at Saskatchewan Glacier. We've got the first ever observation of a subglacial conduit being illuminated by these stick slip events. We have observations that support laboratory findings, and it indicates that unstable sliding is likely a transient behavior for Saskatchewan Glacier. And seismicity is most likely abundant when the subglacial drainage system is well connected and still pressurizes for a given diurnal cycle. So the take-home message for that last one is Saskatchewan Glacier needs to grow its cavities and flood them too in order to have lots of basal ice quakes. So I'll thank the funding agencies and the field team shown here, and I'm happy to take questions when we go to the panel. Thank you all for listening.
Thank you, Nate. That was really great, really impressive results. And it sounds like your cat was really excited by these results as well. Next one up, we have Dr. Kate Winter. Kate is a Vice Chancellor's Research Fellow at Northumbria University in the UK, where she also completed her PhD in 2017. And Kate uses ice penetrating radar to explore ice flow and sediment transport in Antarctica. And I think that's also what she's going to talk about now. Over to you, Kate.
Thank you very much. Yeah, it's lovely to be here. I really enjoyed the IGS talk so far. Yeah, I really liked listening to that last talk as well. So I'm going to talk to you a bit about some of the work that I worked on towards the end of my PhD and that I've been working on kind of since then. So I finished my PhD in 2017, so I still feel I can sneak into the early career talk there. So the work that I'm talking about today is kind of a combination of work that I've been doing with different funders, noted at the top, and different collaborators noted at the bottom. But I think I wanted to explain kind of my motivation for the talk first, and my motivation for this subject. And it's like I have a background in geology and ice, and I'm really interested in how, initially it was how ice was carving landscapes and changing landscapes. But more recently it's about kind of the opposite, and how kind of rocks can move through a landscape and change over time, and these processes that are happening kind of on daily scales around the world. So what I'd like to talk to you about today is radar detected englacial sediments. So looking beneath the subsurface and looking for sediments. So I thought we'd start off quite basic. It's quite nice to kind of pull everyone together in terms of geology here, because these talks aren't quite so prevalent in the recent seminar series. So let's start with the basics. We know that glaciers can erode sediments, and we're used to seeing kind of U-shaped valleys and glacial sediment erosion. We can go off to moraines, and these are kind of examples that we find. Now these are ones from Antarctica. The one here on the left, I think it looks a little bit like a guinea pig. It's got very parallel striations, so that tells us that this rock has been in contact with the glacial bed, with ice. And it's a completely different lithology from the rocks around it. So brown compared to grey for those who are not so into geology. And that tells us that it's been transported through the ice. Now the class on the right has kind of pock marks and striations in different orientations. So it's a slightly more complicated flow path to get to its current site on a blue ice moraine in West Antarctica. So these are evidence that these rocks are entering the glacial system and moving through the glacial system. And then we can look at examples of rocks within the glacial system. And the best place to do that is to book your holidays, head off to Chamonix and go and pay to go in the tunnels that they dig there for the tourists. And that way you can see the class really clearly, these huge boulders within the ice. And what's happened is the glaciers picked up these rocks from up valley and slowly moved them down valley where they're deposited as moraines. So this is the kind of picture that we're used to seeing in alpine environments. We have this very glacially modified landscape where we've got mountains that are slowly eroded by the ice. We see sediments on the surface. But it's not really what we're used to seeing in Antarctica, where almost 99% of the continent is covered by ice, leaving little room for rock. So that means we have to explore beneath the subsurface of Antarctica. So that's where my kind of geophysics background comes in. So I did a PhD in radar. And for those of you who are a bit unfamiliar with radar, I thought I'd put up this plot. It's one that I use all the time in my teaching and research. It's from Rob Bingham, who I worked with when I was an undergraduate. So it's his fault that I'm still doing this work today. He got me interested in that. So this is how radar works. It's a bit like taking a CT scan or an X-ray. You peer beneath the surface and you see what's going on underneath it. So it's this fantastic tool that's been developed for almost 50 years now, over 50 years. And definitely it's been getting improving with age, like a fine wine. So radar works by having a transmitting unit that sends a signal down into the ice, and that pings off layers in the ice, so seasonal layers in the ice or tephras and rocks, and also pings off the subglacial interface as well, so the glacial bed. And the ice is a completely different signature to the bed, so the bed's really clear. These signals ping back up to the receiving unit, that's up here, and what we can do is we can pull the whole system along on a snowmobile, by hand if we want lots of detail, want to go really slowly, or we can put it all up on an airborne platform. So it just allows us to see what's underneath the subsurface in kind of these 2D slices. So what do radar detected englacial sediments look like? Let's look at some radar. We're going to do some radar squinting together. This is an example from Antarctica, close to the McMurdo research station. And what they did here is they did a radar traverse down this glacier here, the Mullins Glacier. And now this glacier covered in sediments. So you would expect these sediments underneath it. So it's a great kind of proof of concept, you know, can we see where these sediments have come from? And the answer is very much yes. In the radar transect below, we see the surface of the glacier here. We also see the bed of the glacier as well. So that really sharp contrast between ice and rock. We then also see these steeply dipping reflectors coming up to the surface, and they match bands in the top of the glacier in the surface. So this is a really good example from Antarctica. We don't have many examples from Antarctica. An example of radar detected sediments in Antarctica. Now, I'm very much keen on looking north as well and seeing what's going on up there, and also looking to the valley glaciers. And I think sometimes we get a little bit stuck if we're in Antarctica and we just keep looking at Antarctica. There's a whole wealth of information out there, and especially when we've not been looking for sediments within the ice for too long, it's really important to head north. So that's what I did in kind of my literature review in my PhD, and I looked at what's going on in Svalbard. So this is from a 2010 paper by Murray and Booth. And again, we've got the glacial surface, and the ice here is much thinner, but we see a really sharp contrast with the bed again. And again, we're seeing these really kind of bright, steeply dipping reflectors. Now, particularly F1 looks very similar to the bed. So we think it's got very similar properties to the bed, as in the bed is made of rock and these radar reflectors are also made of rock. So you can go and read the paper and you can learn all about this, but essentially there's a surging glacier system, and as the glacier moves, it is able to pick up and entrain sediments at the glacial bed. So can we find examples like this elsewhere? Can we find them in Antarctica? Well, I wouldn't be here today if I didn't find some, would I? So we're looking at train sediments in Horseshoe Valley here. So this is my field site for my PhD. I'm very fortunate to be able to go down here for my PhD, part of a NERC-funded project. So I'm looking at Horseshoe Valley here, shaped like a horseshoe. We're in the Sentinel Range, and Mount Vincent is just here, the highest mountain in Antarctica. So ice flows out towards the Institute ice stream, and behind Horseshoe Valley we've got the Ellsworth Trough, where Lake Ellsworth is, just for some kind of context. So the ice is really quite slow flowing. There's lots of mountains around, and therefore lots of sediment sources. So let's take you up onto the mountains then. Let's go up into Horseshoe Valley, and we're going to stand on top of Independence Hills here. Absolutely gorgeous scenery. You know, yeah, what I would do to be back there now. So we can look over this mountain range and we see these huge expanse of sediment deposits. Now these are called blue ice moraines because they're within blue ice rather than white ice that's covered in snow. So there's a process by which blue ice flows to the surface because katabatic winds flow up and over the mountains. So again, if blue ice is something that you're quite interested in, go and have a look. There's lots of literature on it. But essentially, these moraines have gathered here because of ice flow. They've gathered here for many, many hundreds of years, and we've got lots of cosmodates that you can go and have a look at in Andy Hind's paper there. But what happens when we fly a radar across here? So we've got the radar and the Twin Otter for the Institute Mollern Foundation Ice Stream Survey, which is the gift that keeps on giving, in my opinion. So much interesting information in these radargrams. And what the radar tells us is that there's a valley here. So we've got a valley between Patriot Hills and Independence Hills here. We see again that the bedrock is quite different to the ice. And then we see this really quite dark reflector kind of band here. And lo and behold, it links to the sediment on the surface. So we've got some evidence of quite a lot of radar detected here. Those sediments are coming off the bed up to the ice surface because of blue ice flow processes. So we can look at multiple radargrams because there are lots of flight lines in this area. So I've got some examples here. So we've got radar line 1, 2, and 3, and they're kind of, down valley a little bit. The reason we have to look at multiple radargrams is because radar can sometimes trick us a little bit. Sometimes we can get side echoes, and sometimes the processing kind of can obscure features or kind of highlight features that might not otherwise be highlighted. So we look at multiple radargrams to see how they change over time and what the real picture could be. So again, we've got that valley And this time here, you can see these dark reflectors coming up to the surface, reaching the blue ice moraine. A slightly different kind of pattern in number 2 there, and then a pattern number 3 where right at the bed, there's kind of bumps in the bed indicating maybe sediment accumulations, and those sediments are coming up to the surface where we can date them, and we know that they're just coming up at the surface. So yeah, radar detection glacial sediments in the West Antarctic ice sheet, wrote a paper about it. So that came out just 2019. So you're not too far behind the times if you've not picked this one up. But you can go and have a look at it and obviously read this in a lot more detail. But I just wanted to kind of highlight the kind of research that I've been doing and how your research might fit into it today. So we can also do ground penetration radar, and I did that. All this information is in my PhD thesis, which is available online. But it's a much slower process filling radar by hand, but you get such a level of detail. So we're looking at a scale here of just kind of 100 meters under the ice, so right at the margin to see the detail of what's going on. And this is my interpretation of it on the right. So we've got mountains here underneath, there's a bed here, there's something going on here, potentially some loose sediment, and all these hyperbolic reflectors here represent sediment imaged by the radar. And it's just the radar kind of pinging off the sediment, creates these kind of unhappy smiles. But that's telling us how the sediment is getting entrained and how it's being pushed up. And it's kind of pushed up in these zones, a little bit like the thrust zones up in Svalbard. So you can learn a lot about sediments this way. So we've been looking for sediments elsewhere. Could we find them at much greater depth? So we're looking here at a depth of kind of 1.5 kilometers rather than the 100 meters that I was just talking about. The radar processing is slightly different here because we want to focus on the bed, not surface. So ignore the surface there. But what we need to look at here is these reflectors. Like these are the sharp reflectors like the ones that we looked at in the Mullins Glacier and up in Svalbard as well. Could they be sediment reflectors? I certainly think so. I've put a schematic here on the right to try and explain my thinking, which has definitely been shaped by lots of great people, including David Sugden up at Edinburgh University. So I wonder if these are evidence of sediments being entrained at the boundary between cold and warm ice in a valley in Antarctica. So sediments are actually being trained at this exact point here. They're not being entrained up here. They're not being entrained here. It means that sediments are available for entrainment, that they can be picked up by those kind of classic processes that we know about that create these U-shaped valleys. And over time, this thermal boundary might migrate, it might go up, it might go down, kind of based on the thickness of the ice. And we've got lots of examples from cosmogenic dates of the ice thickening and thinning in this area. So sediments are being trained along the thermal boundary here. They're also being shot up into the blue ice moraines here by blue ice flow. So what happens when we go past the mountains then? Well, I wonder if we get passive transportation. So these reflectors, they're no longer connected to the bed because there's no reason for them to be entrained anymore. There's not this great friction as the ice flows past the mountains through this valley. So then the sediment kind of smears out, and that makes it really hard to keep detecting glacial sediments downflow because they're smeared out, and it's much harder for the radar to pick it up. So the best place to find glacial sediments is obviously close to the source area. Now, putting your kind of null processes and kind of even like roche moutonnes and drumlins and all these fantastic features that we see in deglaciated landscapes, even like Scotland, where I'm from, can we find evidence of that in an ice sheet that exists today? Well, I found these reflectors here, again, sharp reflectors extending from the bed in multiple radiograms in slightly different orientations. And what we see here is that I just kind of highlighted this bit here for you. We see these buckled layers. So they're telling us that the ice has to push and squeeze past this bedrock bump. And as it does so, we're getting friction-induced melting, capable of picking up and entraining. So we can do some kind of back-of-the-envelope calculations about how much sediments are being picked up here. But this is just one very small part of Antarctica in Horseshoe Valley. What's happening elsewhere in Antarctica? How much sediment is moving through the glacial system and being deposited? by the ice sheets in Antarctica? It's very much a question that I think I'll be working on for a very long time. So those of you who may be not quite so interested in sediments, and this is quite new to you, kind of you might be asking, you know, so what? Why should we care about englacial sediments then? Well, I'm going to give you a couple of reasons why. Sediments tell us about supraglacial processes. We can learn about erosion rates in Antarctica when we can't go and scan the mountains all the time. We're not on site. Very hard for us to monitor these mountains and changes. So they tell us about kind of rock weathering in Antarctica. They tell us about englacial processes, how are sediments entrained. They tell us about the thermal boundary within the ice that's really hard to determine from any other means. They tell us about some subglacial processes. Are there loose rocks available? Have the valleys been scoured to the point of, you know, that you can't scour much more? You know, are we getting really polished surfaces? Or is there still lots of sediment available for entrainment? And they can tell us about landscape change and ice sheet history as well, because it's those kind of blue ice moraines that deposit sediments high up in the mountains, you know, so you might up here, that can tell you about ice sheet history and change through cosmogenic nuclide dating, which we certainly had talks on in this seminar series. This is the project that I'm currently working on at the moment, and that's why I wanted to really share this with you, what else we can learn from sediments. You know, sediments can also feed the oceans. So how they do that? Sediments come off mountains. You know, we can measure these, and that's something they've been doing with a laser scanner and some seismometers. The sediments enter the ice sheet, flow through the ice sheet, and end up in the ocean. We're picking up sediments at the at kind of bedrock bumps here that we showed before. There's basal sediments that are controlling ice flow in places. And all these sediments are making their way to the Southern Ocean. Now, if these sediments contain essential nutrients, like iron, then that's what we're dumping in the Southern Ocean. So that's the project that I'm working on at the moment, and I'm working on that in East Antarctica, actually, and we're working on the Sorondon Mountains. And I can certainly tell you that there's lots of iron in the sediments at the surface. There's iron-rich rocks on the mountains, and there's iron-rich rocks coming off the blue ice moraines, which we can trace to the glacial bed. So we know there's nutrients in these rocks, and as they're slowly ground up, deposited in the Southern Ocean when they rain out of icebergs, could they kind of enhance phytoplankton blooms and draw down CO2? That might just be a small, kind of very small component of the carbon feedback cycle, but it's something that we've not yet considered. So I'm really interested in working with people who work on the mountains, who work on ice flow, who do all sorts of things and work in the ocean, and seeing what you think about these theories and these ideas that I've been having. So really that's the end of my talk. I just want to say, you know, let's keep an eye out for these radar detected englacial sediments. We see some sediments at the surface. I'd like to map them more, but let's think about what's underneath the surface too. Thank you very much. I'm going to stop my slides there. My email address is there if you need it, but this is all recorded, so you'll find it later on. So do reach out to me if you have any questions at a later date.
Thank you, Kate. Really interesting images and really nice graphs actually that you showed. So thank you very much. Next one up is Jakob Steiner. He is about to finish his PhD at University of Utrecht, which is about mountain hydrology, including studies about ice cliffs in the Nepalese Himalaya and terrestrial ice margins in northern Greenland. And since September, he's also employed at the ICIMOD in Nepal. And actually, Jakob is joining us from Nepal right now, where it is 3 a.m. in the morning. So thank you so much for staying awake for us, Jakob, and over to you.
Thank you very much for having me. Good morning to everyone. Let me share my screen. I hope you can see it.
Yeah.
All right. I'll be talking about vertical ice, about, as you said, about ice cliffs on debris-covered glaciers in the Himalaya, but also about vertical ice along the terrestrial ice margin in the northern Greenland. Why? Simply because when you stand in front of these walls of ice, they're impressive, and you wonder how they form and why they form, and also why they disappear sometimes. And and ask yourselves, whether perhaps they, or I ask myself whether they could give us some clues about the local cryosphere in both these cases. And I'll talk about these two regions based really on insights from multiple field seasons that I was very lucky to join during the last years. And I'll start off with the ice cliffs on the pre-covered glaciers. So those have been mentioned in literature way back, and especially also by mountaineers who had crossed the debris-covered tongues, especially in the Himalaya, to reach their routes. Because these cliffs are impressive when you pass them, but they're also a pain in the ass because it makes it very difficult to actually navigate these glaciers. They were then investigated in more detail the first time, I think, really by Akiko Sakai and her co-authors on Lirung Glacier. That's also the glacier where we work in the Langtang Himal. They looked at melt rates and they really described them in detail, but they have been documented since then in literature in other places as well. The Alps, more recently in exciting studies in Alaska, and stuff is coming out from the Andes as well. But the bulk of the literature is really coming still from the Himalaya. So when we are talking about ice cliffs on debris-covered glaciers, it's very biased towards what we know from the Himalaya. Just to characterize them a bit, they are generally, when ice cliffs get a slope below 30 degrees, then they are covered again in debris. Then they disappear, but they can be steeper than vertical as well. So we have overhanging ice cliffs as well. You will see pictures in a minute. And based on what we see, goes up to 30 meters in height, or sometimes also higher. And then depending on the width of the glacier, a couple of 100 meters in width, with different forms and shapes. The area I'll be focusing on is the Langtang region just north from here, from Kathmandu, where we've been doing many field seasons the last years on the cryosphere and on mountain hydrology, and focusing a lot also on debris-covered glaciers. So that's what an ice cliff looks like. And people who see a debris-covered glacier the first time, they are often a bit underwhelmed because you hope to see ice, and then often you just see piles and piles of rocks. And these glaciers are also a bit annoying to walk on because stumbling over these rocks is not so easy and can also be dangerous. But then these pieces of ice, they pop out suddenly, and often they're like here, they're next to superglacial ponds as well. And you wonder, how does it appear? How does it disappear? And does it tell us something about the state of the glacier tongue that we are standing on? So that's what we have been wondering a lot, and what we've been investigating in the last years. So the hypothesis on their importance were really, from field studies. It was observed already that they melt quite rapidly, but also then on larger scale studies on debris-covered glaciers, it was observed that from DEM differencing, that delta H, delta T of debris-covered glaciers was higher than you would expect, considering that melt below debris is generally lower than on clean ice glaciers. And one, rough hypothesis was that perhaps these features that we see optically on the glaciers, they could be to blame. So there is this exposed ice on an otherwise insulated glacier surface, and because it's not just clean ice, you have this dust on the cliffs, and you have debris that like trundles down over the cliffs. They're very gray, even black sometimes. So they have a very low albedo, which explains also the high melt rates. But on the other side, we have very few direct observations, and aren't there too few of them anyway, and aren't they too small to really play a big role? And also, it has been suggested, so the explanation for relatively low delta H or high delta H delta T for debris-covered glaciers, that it may be the low emergence velocity over debris-covered glaciers may be to blame rather than perhaps these features. all these debates aside, I think they are interesting features, and they are challenging to include into distributed models of melt, because you have ice next to rock, and there is a lot of dynamic movement going on. And for atmospheric scientists, they are exciting because they pose a challenge for the surface boundary layer. So the surface boundary layer on debris covered glaciers, because of this undulating terrain and of the mix of warm debris and cold ice, it's quite it's quite a mess. And then there are many shapes and colors of these ice cliffs. Many of them are they are quite straight, and you see in the upper line these typical lateral cliffs. You can see already that the color changes, right? You have the white and the grayish part. There is an overhang as well. So in this case, this is quite this is really overhanging where this lake was previously, or is now very small. This is a cliff that basically is, after this picture, it disappeared a couple of weeks later. And then you have circular cliffs as well. They form when englacial channels collapse, and then you have a hole forming, and on the side of this collapse, the ice is exposed, and then gradually morphs into the morphology of the glacier surface. So what we do is, there should be another picture to the left. It doesn't appear, unfortunately, but we put stakes, in this case parallel with the Kovacs and the Heuke, into the ice cliffs. We also put sensors of radiation and for wind to understand the energy balance, and then we combined that to try to we measured melt at the cliff and also modeled it. And that allows us to see that there are very high melt rates on these cliffs. So here you see two plots from point scale studies that we did some years back, and so the diamonds that you see here are the stake measurements, and the line in between are two versions of the energy balance model. And you can see over 2 weeks we have half a meter of ice is lost at a specific stake, and that's at another location. But the variability is quite large. So this is from a review that Scott did and Scott Watson did from different studies. So they lose mass between 1 and 10 centimeters a day, perpendicular to the ice cliff. That's quite a lot. So, and that is due, as I said, to the low albedo as well. And we see a lot of exposure to solar radiation at the top, but at the base of the cliff, like where this overhang was as well, there is long wave radiation from the surrounding terrain, and also subaqueous melt from adjacent supraglacial ponds. But now it's a question, how many of them are really in space? And we looked at that with satellite imagery. And here you see from one of our glaciers, 3 snaps in time. On top, there are ice cliffs, and on the bottom, there are the mapped ponds. And here, this is one snap in October, in December, and then in May, so in the ablation season. And you can see that the cliffs, they become a little larger in the ablation season, but they don't necessarily become more numerous, so the number stays relatively stable. While the ponds become larger and also more in the ablation season. There's a lot more meltwater on these debris-covered tongues. Overall, they cover a relatively small part of the debris-covered tongue. So cliffs cover between 1% and 3% of the total area, depending on the season, and ponds a little bit less. Individually, these cliffs become up to 1,000 square meters large. And of all these features, about 10%, we can see them over a whole decade. So they persist, they flow with the glacier, and the rest of them, they are more ephemeral. So they appear and disappear between the different seasons. So from this catchment, at least, even though they're relatively few, the melt rates are so high that we think they do play a significant role in mass loss. But I think we really need a lot more observations, especially from other climatic regions, to be able to say that definitely for debris-covered glaciers in general. And I now jump up to the north of Greenland, to the land-terminating ice, to the ice sheet margin, where we see vertical cliffs as well. This has been documented in Antarctica, very nice studies in the dry valleys, in Greenland, and also in a much smaller scope on the Kilimanjaro. And the land terminating ice margin can be very shallow, less than 10 degrees, but it can be also vertical, so 90 degrees. And it can be quite high, so these vertical walls. and can stretch over many hundreds of meters along the margin. So that's what it looks like. That's from our field site in northern Greenland. So it's, you know, it's quite impressive standing there. This is me and a colleague of mine doing GPR on top of the ice. So this is our field site. For those of you who are familiar with northern Greenland, we work a little, or we went there in 2017, and we flew with a helicopter from the Thule Air Base, which is down here, to the Nunatar ice cap, and stayed there for 10 days doing field investigations. And that's what this is unfortunate. Give me a second. There should be another image. It seems to happen sometimes that the image disappears. But, anyway, this is the more impressive remnant. Anyway, when we arrived there, we knew that, of course, there were other scientists before us, and they were kind enough to leave their toilet, which we could use. And this toilet was, we came in 2017. This was built in the 60s. It was still usable. It missed the door, but that didn't matter so much because nobody actually bothered us, apart from us, from the three of us who were there. The whiskey bottle that you can see here and the toilet paper roll was actually added by another research group that had visited the area just a couple of years before us. And who were these people? So this was exciting work led by Richard Goldway to lead field campaigns there in the 50s and 60s as part of the wider Camp Century campaigns, investigating how to access the ice sheet with heavy machinery. And they have put together really impressive work that we relied on and that we tried to revisit. And I want to point out here the two picture lines. So first here you can see, so this is the picture from 1955, where in the back you have a vertical ice cliff, while here in 2017 the ice margin has become shallow. So the slope is very shallow. We could actually access here by walking, so a lot has changed. And then here on the lower part, you can see that the amber ice, so that the entrained debris that you can see in the ice sheet or in the ice cap, is at the very base of the margin, while in 2017 it has moved up vertically, right? And yeah, this is for a link to Kate's talk perhaps as well. This is, I also think, quite exciting to know more about the entrained debris in the ice. All right, so there are a couple of enigmas. That margin was relatively stable since 1950. It even advanced from the 50s to about 1985, and then it retreated a little bit again, and we can link that to temperature anomalies in the region. It is sometimes steep, vertical, and sometimes a ramp, and we did a GPR on that whole part, compared it to PadMap as well, and it really seems that behind the vertical part there is an over deepening, while here there is not, but this will really need more ice dynamic investigations that we hopefully do in near future to understand this better, why on one part it's vertical and the other one it's not. And then finally there is this amber ice, and there is a very nice study that was recently published by Joe McGregor and his colleagues in Journal of Glaciology as well, where they have compared these amber ice lines here with debris from ice cores from the ice sheet, not exactly at this location, so generally all over northern Greenland, and this matches really well. So this shows that, you know, these amber ice lines here are a nice window into the past and could potentially also help us to better understand past ice dynamics, and then also understand why the ice margin is forming in this way along the land terminating ice margin in Greenland. And that's already everything from my side. I hope I didn't keep it too short, and I will actually end my presentation with the introduction of next week's speaker, who is also going to talk about the ice margin in Greenland, more the ocean terminating one. On 10th of February, Michael Wood is going to talk about the OMG project in Greenland led by NASA. Thank you very much, and looking forward to the discussion.
Thank you, Jakob. Really impressive results. I was really impressed to see those images that you shared of the older days and the more recent photographs. Thank you very much. I think now it's time for questions. I think the easiest way would be if you would indicate that you have a question either in the chat or by raising your imaginary hand. and then we can just ask you to ask your question, and you can unmute yourself. I think we already have a question by Roger for Kate. Roger, do you want to ask the question?
Yes, I'm happy to. Thanks very much, Rebecca, and thanks, Kate. Enjoyed that very much. I was just aware that those diffraction hyperbole you showed in your data obviously need an object of a certain size to be there to create the hyperbola. And yet in other areas of the images you showed, you know, the radar image was kind of grayed out, which suggests there's an awful lot more smaller stuff there. I wonder if you have any sense of how much smaller material there might be there, because the rock content will change the radar velocity, presumably, which you might be able to detect from the hyperbole.
Yeah, it's certainly something that's interesting. So I definitely feel that it's very unlikely that there's a single boulder that's producing these hyperbole. It's much more likely to be a cluster of them. But the good thing is they come to the surface in the blue ice moraines, so we could actually take the sediments, and we actually took loads home with us and sieved them all. And it's something that a postdoc on the Blue Ice Project did. His name was Matt Westerby, and Matt's got 2 papers out on the Horseshoe Valley blue ice moraines. So he's done all the analysis and got all these D50 charts and everything to look at this. And yeah, the answer is yeah, there's lots of really small, fine material, and there's lots of big clusters as well. And the way that they come up in the moraines, there tends to be kind of ridges of the larger class and ridges of the and kind of depressions of the smaller class. So we do see that at the surface. And I think it's just the difference between the 2 radars as well. It's the airborne, just going to image things slightly different and kind of cut this kind of mass compared to the ground radar. And that's why I quite like using both techniques to try and learn more about it. So yeah, the blue ice moraines are really great because they do allow us to see what's come up from the bed and explore that more. So yeah, lots of finds, but then some really big boulders too. And they've got striations on, so we think they've come from the bed rather than from the mountains down.
Smashing, thanks very much.
No, thank you, it's great.
And I think we got another one from Trevor, and I assume that is for Kate as well. He's asking, oh, Trevor, do you want to ask yourself? I'm happy to read it out. Okay, so Trevor is asking, does your study relate to roche moraines suspected of forming at the cold-warm ice boundary?
Yeah, thank you very much for that. It's great to kind of really link in with the more paleo community here and the geomorphologists, because they're something that we certainly see in kind of like post-glaciated landscapes, you know, like up in Scotland, rather than things we particularly are seeing in Antarctica. So we're certainly always trying to make links between the two. In terms of my understanding of Rogan moraines, and do correct me if I'm wrong, but they're transverse to ice flow, and that's not necessarily what we're seeing. So certainly when we image the blue ice moraines and we image along them, they're coming up parallel to the ice flow. So they're coming right up at the margins for the blue ice moraine rather than being transverse to ice flow. So we wouldn't get the same pattern. But then the ones at depth, I think they're also coming up in a kind of plane. But it is really interesting to try and think, well, what would happen if the ice was to melt, and what kind of patterns would we see? And the other thing is, I suppose, Rogan moraines, we all think of them about being kind of at the base of a valley where there's lots of sediments, rather than at the side of a valley. But I certainly understand your argument of the kind of the cold, warm transition and what it can tell us there. So that's something, yeah, that I'm certainly interested in. And it's quite hard, isn't it, to get that 3D picture sometimes. Certainly something I'm working on. And it'd be great to have multiple radar lines to explore this in more detail. So yeah.
So have any Rogan moraines been detected in Antarctica?
I'm not entirely sure. I think there's lots of interesting features in the Rutford. So that's certainly where I'd go looking if I was going looking for them. And the Rutford's very close to this valley as well. So that would be my first place to look, I think. And lots of radar there as well.
Thank you.
Well, thank you.
Great. We also have one for Jakob from Eric Peterson on Facebook. And he's curious to hear more details on the logistics of steam drilling on ice cliffs. Are you lowering from an anchor of ice screws, and how do you keep the correct dip angle on the drill bit through horizontal drilling?
Yeah, good question. I mean, it's just for the process. We originally started with the Kovac, since that was logistically naturally easier to do. But because of the entrained debris, and there is of course a lot on, I don't know if Evan is listening, or is anyone from the Everdrill. They would be the guys to talk about that more in detail. But there is enough in those ice cliffs as well that you get stuck all the time. So at one point we also then switched to the Heuker, to steam drilling. How do we are actually anchored? Yeah, so we are anchored on the top of the ice cliff to boulders, and then we lower ourselves down. How do we keep the correct dip angle? By trying really hard. It's not always easy to do that. We sometimes also had to re-drill repeatedly because it was not possible. But we had you call it the angle meter constantly, so that the guy who actually is drilling is checking the angle, is making sure that it is perpendicular to the ice surface constantly. But yeah, it's tricky business.
Okay, great. Do we have any more questions? Another one from Roger. This one is for Nate. He missed the start of your talk. Do you have any focal mechanisms?
We've started doing some focal mechanism work. Unfortunately, because of the geometry, it's hard to come to very tightly constrained solutions for where the most active clusters are, but in general, we're seeing something that appears to be double couples that are well aligned with the bed.
Thanks. That's interesting. What are you using for such mechanisms as you can get?
It's manually picked first motions after doing necessary instrument response removals, and then hash. Okay,
so just polarities, because there are some nice codes. Sorry, I have a background in nuclear test band seismology, and we got very, very vexed by issues of finding focal mechanisms with not very much data. So there are some interesting codes out there that might use more than just the first motion at some point, and that would be a really interesting avenue to take forward.
Absolutely.
Cool. Thanks a lot. Good luck to you.
Cheers.
Okie dokie. I think Hester did just post a link to Jacob's Greenland ice cliff paper. And Nate, do you have your stuff published as well? Or is that something in progress?
In preparation.
Okay, amazing. Looking forward to that. Oh, we have another question from Trevor to Nate. Are your Greenland cliffs formed by marine abrasion? I don't know how to pronounce
it quickly. And I would have thought that some of the cliffs might be higher if they were at the sea level.
That is for me, I guess. So yeah, they are the Greenland cliffs where we work on. They are a lot higher. So I doubt the marine abrasion has something to do with it. But so we have also looked at the complete ice margin, the terrestrial ice margin, where these kind of cliffs are also closer to sea level. So I could imagine that this may play a role. But I must say I've never been to a location where it was close enough to sea level.
Okay, thank you.
Okay, any more questions? Last chance. Okay, if not, thank you to everyone for attending, and thank you to the three speakers of today, Kate, Jakob, and Nate. Thank you so much for your contribution. That was really interesting, and I'm really looking forward to more early career scientists who giving a talk. So if you know of anybody, please do encourage them. And with this, I think the only job is to say, see you all next week, and thank you for joining.
Thank you very much, Rebecca. I enjoyed the other two talks, really great. Thank you.
Thanks very much to everyone, and see you next week at Mike Wood's seminar, same time, same place. And thank you, Rebecca, for sharing.
Thank you. Bye now.
Thank you. Bye-bye.
Thank you.